Hello, community! We have to stop AI overthinking because if we pay for each and every single token, hey, come on AI, I just want to pay if it's absolutely necessary that we go in a complex overthinking mode. So let's increase the complexity and we do two papers at the same time. You might ask why? Because A, we want to have fun. Second, look at the date. May 19, unbelievable. And it is about the same topic. Reasoning models can learn when to think, and language models learn when to think. This is here by Tsinghua University in China, and here we have the National University of Singapore. And I think it's so beautiful to have the identical topic on the very same day. So let's see what they address. And yes, for both we have a GitHub, you have the code, you have the data, you have everything available for you. But just let's start here. Let's start to think about this. So very first model here, Tsinghua University, China, beautiful paper. And they demonstrate here the advantage of not thinking, of no thinking modes over the thinking mode, the reasoning models, where you have multiple thousands of tokens in a complex thinking structure. And they say, you know what? Maybe we don't need always to have this complex thinking mode. Look at this. This is an example. They have here a simple question from a particular benchmark. And then you have here the DeepSeek R1. And we go with a distilled Q17B. And you see it takes 3,300 tokens because we switched on here the thinking mode, complex thinking. It's beautiful. Yes, it's gorgeous. It explains everything. But do we need this if we just want to have the result? So, and the authors tell us now, hey, we propose now a new methodology called AdaptThinking. AdaptThink. This is a novel reinforcement learning algorithm. We have a look at detail about this to teach here the reasoning models, or R1 models, or a distilled model here, when really to switch on here the complex thinking mode, but maybe the system is able to do it without here reasoning. Because look, if we take here this AdaptThinking 7B, this is the model that they built. It's available for you, free of charge, no problem. They only give also here 222 tokens. Isn't this nice? So, what is here the main core? And I looked at the paper and I looked at the optimization objective and I looked at everything on a constraint optimization problem and with the penalty weight here. And I said, okay, and the pre-sampling by training and then the optimization objective becomes here this. And then I said, hey, wait, here, this is it. Look at the advantage function that we have here in the report. This is now here interesting because you see we have here our end of thinking here with a particular hyperparameter delta. And now it turns out if you adopt a non-thinking mode more frequently, if the delta is increased. Because you say, hey, end of thinking, that's it. So we go here, and this is so simple. We go with the classical OpenAI PPO style. We even say, hey, without a Kullback-Leibler penalty, and we have a very simple formula here. And yes, of course, a little bit of clipping, but this is our PPO. That's all we need. And then there's something crucial because they need now an importance sampling. Why? You remember reinforcement learning? We have here an initial reasoning model. So a reasoning model that will always choose here the thinking mode. Yeah? And it's quite hard to get it now in the non-thinking mode. This is what they called a cold start problem. So if you have now this AdaptThink, the samples now from a modified distribution that ensures a certain proportion, let's say 50% of responses start now in the non-thinking mode, by forcing here the end of thinking as the first token and the rest is in thinking mode, we can have now a much nicer sampling if we have the non-thinking and the thinking for our sampling procedure. Because this allows the model to explore here and learn both modes from the beginning here after reinforcement learning training. Very simple. This is it. This is all there is. So we have two components. A constraint optimization objective. I'll show you here the formula from the original paper that encouraged the model to choose here the non-thinking while maintaining here the overall performance. And then we have an sampling strategy that balances now the thinking and the non-thinking. And this allows the model to explore and exploit. Remember, we have both this beautiful, delicate equilibrium. We have both thinking modes and non-thinking modes throughout here the training process. Now you remember, huh, that just some month ago we had here this beautiful paper from Berkeley, University of California, and Allen Institute of AI about reasoning models can be effective without thinking. And at the time I thought, hey, wow, hey, how can they dare to say an LLM can be effective without thinking? But then we discovered here, if the problem is simple, we don't need here the complex reasoning models. So the benefit of thinking come really into play, they become pronounced when the problem is difficult enough. Otherwise, our LLMs are so good already that they can generate a solution without activating here reasoning. And they say now here this AdaptThinking, this new model here, this novel reinforcement learning algorithm here, based here selective on a problem difficulty. And you immediately understand that this is all about the dataset, the training dataset. So what they say, okay, let's start here with a DeepSeek R1. And we have here, because they have to do this here on their own budget, the 1.5 billion and the 7 billion model. Yeah? And then for the training dataset, they have to create this. They use here the DeepScale R, which consists of 40,000 mathematical problems drawn from AIM, and you know this. And for the evaluation, we use here 3 mathematical datasets with increasing difficulties, and these are our standard datasets, so everything standard. Interesting, they tell us here about the training time. So they say for the 1.5 billion model, we use here just 1 node of 8 times an H800 NVIDIA GPU and about 32 hours. And for the 7B model, we activated here 4 complete nodes here, each with 8 times an H800, about 28 hours, and we just trained for 1 epoch. Now let's have a look at the benchmarks. Now here you have the evaluation, beautiful, and then you see here for the 1.5B and for the 7B here, always in the last line here, a little bit in pink, you see here, okay, this is now the accuracy, this is the length and a specific ratio, never mind. But yeah, it's really performing quite good. You see here other DPO overthinks quite a lot of other ideas, quite a lot of other models, but they tell us here, hey, our model here really outperforms all the other models. And they say, in general, all those benchmarks, we can reduce now the response length here, thinking and non-thinking, by up to 50%, 53%, or the smaller one, 40%, while also sometimes it's great because we can even increase the accuracy from 0 to 2.4%. Okay. But I think here, this is about cost reduction, because we pay per token, and especially if you have models that are proprietary models like OpenAI, this half the token length can be quite interesting. Now, as I told you, we have a GitHub repo just done yesterday, 11 hours ago, to README. You have everything available, and it's an MIT license. Go and have fun. But notice that there's a limitation, because they only train the model using the mathematical dataset, because they need here the easy verification, was the answer accurate, and we have to have verifiable reward structure for our reward models. Now, just another idea, because, 3 days ago I read this. This is from Stanford University, Together AI, and University of California, San Francisco. And they said, you know what? We looked here at medical AI, medical LLMs. And we found that it's important to disentangle the reasoning and the knowledge in the medical large language model. Because they say people, and those people who code the model, they mix up something. They mix up reasoning and knowledge. And we have to disentangle here the reasoning-heavy question from the knowledge-heavy questions, and they did this on 11 biomedical Q&A benchmarks. And they found, and this is interesting, that only 32% of the benchmark questions were really about reasoning, complex reasoning. The rest was not on reasoning at all. So we learn here, coding AI, about our own language, about the semantic complexity and the taxonomy that we should be much more careful to use when we talk about what is reasoning and what is knowledge, and what do we train our LLMs on. Because it turns out it was not reasoning. So they observe here a performance gap. If they look here, hey, what is knowledge and what is reasoning? And as it turns out, a lot of things were just knowledge and not reasoning. And therefore they conclude, hey, it's so important to incorporate additional reasoning-rich data sources here for the training of your model. And they give here a beautiful idea here. They say, what are the knowledge-heavy questions? No? And of course, if you train a model or if you're here in the development of AI, you are not here an expert in medical whatever. So I see that it happened, no? But now they come out and say, hey, wait a minute, no? Patient presented to the hospital with severe conditions. So what is the diagnosis now? This is not reasoning. This is knowledge. Because reasoning-heavy question would be, a 40-year-old mechanics presented this with a particular temperature, a pulse frequency, a blood pressure, a respiration rate, and his oxygen saturation. And then, now, what is the best treatment? This is not about reasoning if we have all the data. This is about knowledge. So you see, now, I mean, can you imagine, May 16 that Stanford published this, and it tells us, hey, the medical LLMs, they mix up reasoning and knowledge. And I love it. Okay, this was the end of paper 1 with some additional papers. Just to have fun. Let's come back to paper number 2. LLMs learn when to think. This is by Singapore, and they propose here think less. Now, interesting, it's also a learnable framework that empowers an LLM to adaptively select between short form and long form reasoning. So you see, it is not anymore about no reasoning at all and long reasoning, but now we have another differentiation, short form reasoning, and this is also for the cost that we have to pay on LLM, and the long form reasoning. Plus, it is based on the task complexity and the model's ability. I love this. Let's have a closer look. So also important to see, it's also a reinforcement learning paradigm. And now what it does, it employs now 2 control tokens. Please remember, control tokens, they will become important just in a minute. And we have one for the short, concise response and one for the thinking, for the detailed reasoning. Now it turns out, and this is really important, they cannot go with the regular GRPO because we have that the system collapses. And now to understand why is important. So they tell us now here, the core of our method is now a new GRPO, a decoupled group relative policy optimization, which decomposes the learning objective of a hybrid reasoning system into 2 components. So we have the control token loss function and a response loss function. If you want to see more about this, also just 20 hours ago, 7 hours ago, here you have everything. This is the GitHub repo for you. But let's have a look at this. So they decoupled GRPO. They need this here for, remember the control token? At first they have the mode selection. Should we go with the thinking or with the long thinking or the short thinking, the concise thinking? And then for the objective 2, then in those class, they have to have the accuracy improvement optimization methodology. Because look here at the dataset. And it's so funny because they use the identical dataset from paper number 1. So we can really compare this paper. Yeah? Look, you see that very simple benchmark, also simple benchmark, yeah, 50-50 benchmark. A little bit more complex benchmark, you see in gray the short mode. Here, very easy, you can solve quite a lot just with a short reasoning. But the more complicated it gets, then you need really here the full thinking mode. And this shows us our benchmarks are saturated. So therefore, I'm so glad to show you today, May 20, this is the day I record this, we have a new benchmark. And my goodness, this is ARC AGI 2. So now a new challenge for a frontier AI reasoning system. And if you think, hey, I know 1, so how complicated could 2 be? Here are now the data. Look, with the new ARC AGI 2 benchmark, you see Claude 3.7, even with an 8K activated thinking mode, achieves a performance of 0.9%. O1 Pro also 0.9%, and the best one is here 0.3. Achieves here a 3% success rate. So I think, yeah, beautiful. We have a new hard benchmark. So this will be amazing. So we will see now here. Have a look at this publication. I cannot go into the details, but have a look at it. I love it. But we know this. I showed you in my video about the new Q1, the 3 model. Now, if we had a look at the mixture of expert model with 235 billion free trainable parameter, with active 22 billion free trainable parameter, I told you we have this thinking mode. And here we have a slider. And we can control the maximum length of thinking. This is more or less, if you want, our token length that we want to pay for. So you have a thinking budget, and you have this in time, in complexity, and in US dollars. And you see, you can move it around. And I have, for example, 21K token. Thinking is really great. So if you want a budget and you want to say, hey, I don't want to overpay here, if you have some complex structures, this is exactly what we are talking. And now we want that the AI itself decide, hey, what is the minimum budget to get here to the right answer? So we are back here to National University of Singapore. The question is, can an AI, an LLM, learn to decide when to think, when to activate complex thinking, guided by the complexity of the task and its own capability? And the answer is yes. So, yeah, I talked to you about we have a problem if we go with the regular GRPO. Since the response part often spans hundreds or thousands of tokens, as I showed you, 21K, and the length of the long and the short responses vary significantly, the single control token that we have at the beginning may receive now weak or biased gradient signals. And this leads, if you look in detail at this, and you see this in the paper, to a mode collapse at the early stages of training. So classical GRPO does not work if we have a, if you want, split mode hybrid system. So this is really important. So from another perspective, the model develops here in the classical GRPO an excessive preference for either the long or the short outputs during the beginning of the training, because the gradient or the control token is normalized by the total length of the response, which here introduces an imbalance between the long and the short outputs. So the long chain samples, due to having here simply more token, receive here a slower update on the think token, while the samples encouraging here the short dominate now the update. And this is an imbalance, and this imbalance causes now the model to collapse rapidly. So the solution was to go with GRPO, but to have here, if you want, a decoupled but interdependent GRPO. You remember in the first paper we also had 2 components. Now here we also have 2 components. What a coincidence. At first they have a mode selection. Do we go here with the quick policy adapt here on the model accuracy, and then if we selected a mode, in those mode we go now for the accuracy improvement. Simple idea, no? Inherently interdependent, of course. So let's have a look at this. We have here our beautiful model, and you see here from all the tokens, we have now the control tokens, think and short. So if we go now with our decoupled GRPO, what is the reward structure? What can we have in our control token think? We have the correct long, so we have a reward 1 minus gamma, and gamma is here a short, a very tiny element that we need here. And we have the wrong response. So wrong is simply here in the reward, in a binary reward model, -1. And the same is for the correct short and the wrong short. So the reward system is predefined. But of course, yeah, this is here what's really playing here. Followed reinforcement learning, decoupled GRPO separates the training in 2 objectives, optimizing here the control token for effective mode selection, and then refine the response. Let's have a look at this. So we generate now a synthetic pair, a data set. Everything starts with a data set. Now we have a data set here with the thinking and with the short thinking, if you want. Each response is prefixed with this control token, either short or think, that conditions now the model on the intended reasoning style. And then we go here, supervised fine-tuning, and we fine-tune the target reasoning model pi theta on this synthetic pair data set via supervised fine-tuning. This is our classical Hugging phase supervised fine-tuning. because the objective is to learn here multi-style response distribution conditioned here on the control token. And either it's short or it's the long thinking mode. You can call this a distillation phase. I'll show you this in a second, that the model is capable of generating both type of responses here with a high fidelity. And the paired construction ensures that the model response distribution will be balanced and we will have no collapse of the system. So what we do, we start here with an intelligent supervised fine-tuning, and then we go to the reinforcement learning. This is our classical path. There's nothing special about this, no? As I told you, at this distillation phase, the model can produce both long and short form answers, but what it lacks is here a deciding mechanism, here a control mechanism. Which reasoning model here really suits here a particular input, a particular task, a particular query that I have here as my input. Remember the slider here with Q13? Now the system should decide and go for the cost-effective solution. This is not easy because the complexity of my input X might be not that trivial. So therefore you have to provide enough and good training data. The quality of the training data must be good, and especially here domain specific if you have a higher complexity level. Beautiful. Control token, reasoning mode, you know already all of this. Yeah. And now, maybe in the next iteration with Q13, you see here we have the freedom as a human to say, okay, this is the amount I want to pay, the length of the thinking, of the reasoning complexity, but this, the next step, the optimization should be done by the AI itself. So here we have it now, a decoupled policy optimization, a simple reward function, GRPO-based framework. We have here the objective is defined in a classical way, token level surrogate loss formally by, beautiful, yes. And now have a look at the advantage function. Look how easy it is now. You see, a complete different function now. Standard deviation, yes, and then we have now, if we go now here into this control token and response token with different normalization, this is now the formula that we simply insert. You can go either with a Kullback-Leibler divergence if you prefer, no problem. Response accuracy are independent normalized, beautiful formulation ensures that the control token receives now a consistent gradient scale across both short and long sequences, addressing the mode and sync short imbalance. So this is the solution, and please notice here also in the paper 1 we had a hyperparameter delta, now we have the hyperparameter alpha, and they tell us here, hey, we experienced here, if we set alpha to a particular numerical value, we have a stable training, we achieve it. Great. So, step back, short summary, what we do. We have to create, very first step, a data set. No? And the data set is exactly what we want the system to learn. So, a synthetic data set. The data set is created using here 2 expert models, LLMs. We need a strong reasoning model for the long form responses with prefix with think, and an instruction following modeling for some concise short answer prefix with short. And this teaches now the other model to generate both styles conditioned on these control tokens. And what the authors did was nice. They said we employ DeepSeek R1 QN 1.5 billion free trainable parameter as the base model to train now the hybrid reasoning policy. So let's do this. So as we say here, okay, the first reasoning model with the thinking control token, they say we go with the full DeepSeek R1 671 billion free trainable parameter. They are beautiful. They generate here the long form data from an open source data set, very well suited for multi-step complex reasoning chains. Great. So first point, okay. Second point, we need the short one. And they say corresponding short form answers are derived using a QN 2.5 MAD 1.5b instruct and instruction tuned models optimized here for concise mathematical responses. So we have here all 3 LLMs perfectly attuned to their function in this concert. And then they say, let's start. So for the hybrid model, have now the supervised fine-tuning, enabling here to accommodate both long and short-term reasoning scales. And we have here the decoupled GRPO. Then the reinforcement learning, beautiful. For this data set, exactly like paper number 1, we have the deep scale art. We have 40,000 label examples here. So the quality of this data set defines everything in your system. And for the evaluation, we use the same mathematical evaluation dataset like in paper 1. Here again, AIM24, Minerva Algebra, Math 500, great. And you see here a lot of different values here, chain of thought valve. This is here with a LoRa adapter with different hyperparameters. But you see here, if you look here at the last one, ThinkLess, you see here bold. Yeah, so they achieved here, with one exception here, the best solution, the best performance of the models that they tested. Also, they say, hey, we can reduce here the amount of thinking tokens by 50 to 90%. So the cost will come down. This is something to be much more cost effective. And here at the end, of course, again, here, the authors themselves with their conclusion, they say, yep, reinforcement learning, we build a hybrid reasoning model, autonomously decide whether to generate a short response or engage in a long-form reasoning sequence based on the complexity of the input query. Core, they use a decoupled GRPO, which separates the reinforcement learning objective into the two components, either the mode selection on the control token, this is step 1, and then, if we have defined here the mode, the accuracy improvement on the response tokens. Beautiful, stable, effectively reduces unnecessary long-form reasoning because the models are so good. They are trained on the complexity levels that should be enough for quite a lot of standard everyday problems that you account. And only if you go in science that you say, hey, now I need long-form reasoning. What's really nice is now LLM can indeed learn to adaptively select the reasoning modes with those systems. Now, of course, this was done here by university. So as you see, we have a 1.5 billion model or the 7B model. If we go to, I don't know, 72B model, I think the performance will increase. We have no idea yet about the scaling laws for these particular models. But really interesting after we looked at the reward model, the LLM model, and now here, this, if you want, adaptive selective reasoning models. Plus, LLMs can be taught to produce high-quality short-form answers through this distillation, through supervised fine-tuning, even if they're pre-trained, focused here on longer generation. Remember, we always start here with a reasoning model, an R1 model, and R1 was trained here on a long, complex reasoning sequence. But now we can help them to produce high-quality short-form answers, which cost less. Great, this is it. So for the last 5 seconds, let's increase the complexity to the max and let's compare both paper. So if you have this both paper here, you see both, you understand here completely the flow and the data and the hyperparameter and exactly reinforcement learning. And you say, okay, let's compare them now in their most effective way. Here we have the second paper and then AdaptThink here is the first paper. Now let's compare them. Efficient mode definition. We just went through the short token, distilled from a specialized short answer, the control mechanism either to generate here the think or the short as the first output token. We have a two-stage mechanism, supervised fine-tuning, distillation, and then a DGRPO modifies here the GRPO objective to rebalance the gradient signals, especially for the control tokens. The key hyperparameter is alpha in DGRPO and mitigation of mode collapse here with DGRPO. And we have a beautiful learning curve for the mode preference. The first paper, AdaptThinking, we have a pure no thinking, which would be a no reasoning mode, induced by an empty thinking segment. First generated token is end of thinking. Learns when to allow here the fourth start of no thinking versus the standard thinking start. We work here with reasoning models. Relies on the base model being a thinking model. A reasoning model would be more correct. And the no thinking behavior is bootstrapped during the reinforcement learning via, as I told you, specific prompting, specific importance sampling, and specific definition of the objective. We go here with the classical PPO style, so a much simpler way with value function and so on. With constraint optimization and importance sampling, we have the hyperparameter delta. Importance sampling ensures that the no thinking mode is also explored. Delta is here You have to choose delta carefully. Key hyperparameter is here in the advantage function here. This delta directly biased towards no thinking if the performance holds, and effectiveness of simple no thinking. So whenever you have some simple task, a no thinking, a no reasoning mode would be enough given the powerful LLMs. But with this methodology, and you have the GitHub repo, you can choose your hyperparameter delta here as a trade-off controller. And yeah, I showed you here the benchmark study with compare the thinking to no thinking, the performance here of AdaptThink. So what a coincidence here. Tsinghua University and National University of Singapore at the same day, at the same topic, different solution. It is so great. If you look at this, you see what you can build in AI is simply amazing. If you have a deep understanding of what is happening, you can build solutions that are just amazing, that are simple to implement, but are quite powerful if you are, for example, like here, cost efficient. You want not to spend too much money here on real complex reasoning path when we do not need this high reasoning capacity for simpler everyday problems. Quite nice. I hope you enjoyed that we did 2 papers at the same time. If you like this kind of video, why not subscribe? And I see you in my next one.